Day 2 of your 2.6 notes modeling with functions. First problem says an open storage bin with a square base. Since the base is square, I start with a square base, and that will be my open bin with a square base. Since it's open, I would not need the top. All I need is the side. This is the bottom and the side. Well, on this side, I will name this one X. If this is X also. This is X, this is X, because it's the square. This also is X. I have X here, I have X here, and X. The other side is the small one. I can call it Y, or Y, and it's Y everywhere, actually. So, now that I know it's an open base, as soon as I see open, I think of surface area, and it's 108 square feet of material. So the total surface area, I will say SA, is equal to 108. Determine the box dimension if its volume is to be maximized. Now, how did we get that surface area? The surface area would be the square that is on the bottom, meaning X times X, which is X squared, plus XY, which is the area of each side here. But how many of it do we have? A total of 4. This is equal to 108. So if I want to solve for this, by the way, Y is represent my height here. If I solve for Y is equal to H. If I solve for Y here, I will end up with 108 minus X squared over 4X. Using your calculator and find the maximum, you will end up with the maximum at 6,108. Since the maximum is at 6,108, it means that the base is 6 feet by 6 feet, and the height, since I can use now to find the height, which is Y, is equal to 3 feet. Let's look at problem number 2. It says this is totally made up, first of all. However, let us believe that it takes twice as much energy for a plane to fly over water as it does over land. We are flying into a city and we are currently 100 miles from the nearest mass of land. And the city is 25 or 250 miles down the coast from that nearest point on land. To what point should we fly in order to minimize the total energy expended in traveling to the city? I will start by the position of the plane, which is here. Straight down, I will have a total of 100 miles. And let's say we start here. This distance is actually equal to 250, the whole thing. It's 250. And by the way, this is the length. It's 250. Now, if this is 250, I can break this into 2 pieces. This being X and this being 250 minus X. By the way, I'm breaking it right here. We've seen a problem like this before. To find this missing portion, if I sit only in the triangle, this missing portion is the square root of 100 squared plus X squared. Alright, by the way, this here is the water. Alright, let's go ahead and solve this problem. It seems like 250 miles is labeled already. I label my 100, which is this side. So I will say the distance is equal to find the total distance, I will have is the total distance we start actually from here. This is what I need to know. But that distance is not just a regular distance. The one above the water will be double because they say it takes twice as much energy. So I will double the distance above the water, meaning 2 times the square root of 100 squared plus x squared. And the distance on the length remain the same. So I will go ahead to this one. I will add the 250 minus x. Once again, I'm using the fact that it takes twice as much energy here. So the distance on the water should be double. All right, from here, use your calculator and you will find that the minimum at this point would be 57.735 and 423.205. So the final answer, if I want to use words here, I would say it will be 57.735 miles down coast. Let's move on to the next problem. The next problem is a little long, not quite long, just a lot of words. You are standing at the edge of a shallow moving river, which is 1 mile wide. So if you're starting on top, at the top, it's usually a right triangle here. I assume it's going to be something like this, but I'll keep reading. But I know that this is 1 mile. You know that it is dinner time because you smell the yummy hamburger on the grill at your campsite across the river. You can swim at 2 miles per hour and walk 3 miles per hour. All right. You must first swim across the river. So let's say this is the river and this is the land. Let me extend that land. And this is the land. So you must first swim at 2 miles per hour and walk at 3 miles per hour. You must first swim across the river to any point on the opposite bank from where you can walk to the campground, which is 2 miles from the point. So this tells me the distance from here to here is 2 miles. And if this is 2 miles, we can use the same concept we did on the previous problem. This is x, this is 2 minus x. From here, I can find the distance on the river. I would say this is 1 plus x squared. At this point, I know distance is equal to rate times the time. So the time itself is equal to the distance over the rate. The time is not just the distance over the rate, but the distance over the rate for the swimming plus the distance over the rate for the walk. So let's go ahead and have an equation for that time. For the swimming, he swim a distance of square root of 1 plus x squared for a certain amount of time. How long does it take? 2 miles per hour, so the rate is 2, plus the distance on the other one is 2 minus x, and the rate here is 3. Using my calculator, I will go ahead and find the minimum of this, and the minimum will be at 0.894, 1.039.